Catalysis. So we've been looking a lot about the rates of chemical reaction, and we see that we can control the rate by changing the concentrations or by changing the temperatures. But both of those methods of controlling the rate of a reaction have limits, right? If you're trying to increase the rate of a reaction, you might be limited by the solubility of one of the reactants. You can't make it more concentrated. The temperature has limits. If you get it too hot, you might decompose your reactants, and that's not going to work. And when we look at reactions that occur in living organisms, the limits are pretty significant, okay? Your body is going to maintain pretty closely a temperature of 98.6 degrees Fahrenheit, right? And so you can't say, well, I need this reaction to occur faster, so we're going to up the body temperature to 150 degrees Fahrenheit.
Yeah, and give yourself a fever body hour.
Well, that's more than a fever. That's definitely going to kill you. So your body's not going to do that.
Wait, what temperature did you just say, right?
150.
100 what?
150.
Oh, yeah.
Yeah, that would kill you.
Yeah.
105 you can handle. 106 even. But 150, no. That's why I chose that, to be ridiculous. So we can't control the rates of reactions that way. But your body depends on being able to control chemical reactions, right? You haven't eaten for a while and your blood sugar's getting low and your brain is saying, I need energy here. And so your body needs to start doing some reactions that it wasn't doing half an hour ago. How does it control those, turn them on and off, make them happen at rates that are helpful? So catalysts. So a catalyst is a substance that increases the rate of reaction without being consumed. It is not a reactant. A reactant gets used up. A catalyst does not get used up. So a catalyst can speed up many, many reactions. It's going to last a long time. And the way they work is by providing an alternate mechanism in which the rate determining step has a lower activation energy. So we just looked at the mechanisms and there was always this slow step. If you can lower the activation energy on the slow step, the whole reaction speeds up. And that's what catalysts do. And this is there's an entire industry of finding catalysts for desirable reactions. Of course, catalysts also are present for undesirable reactions. So here's an example of an undesirable reaction, the decomposition of ozone. So we just looked at that one, right? Pocket lint. So ozone reacting with an oxygen atom to form oxygen molecules. So the uncatalyzed reaction is occurring by this single elementary step. The activation energy for this is pretty high, and so the rate of the reaction is slow. So it's the blue line here. So you go through a transition state involving these two particles, and then you've got your reactants forming. But the activation energy is significant. So the ozone layer does not rapidly decompose on its own. It's pretty stable. But chlorine atoms allow another pathway, another mechanism to occur. And that mechanism has a lower activation energy, and so then the decomposition of ozone is faster. So it's the chlorine atoms that are giving us trouble. So here's a mechanism for the catalytic destruction of ozone. The chlorine atom reacts with the ozone molecule, and it forms chlorine monoxide and an oxygen molecule. That chlorine monoxide reacts with an oxygen atom to form the chlorine atom again and an oxygen molecule. So the overall reaction here, the ClO is an intermediate. Whoops, I don't want to do that. So we've got O3 plus O making 2O2. That chlorine atom doesn't show up in the overall reaction because it's not a reactant, it's a catalyst. It gets used and then regenerated in the process of the reaction, so we don't ever use it up. So the rate limiting step in this mechanism has a lower activation energy, and it's much faster then. So based on your knowledge of the standard states of elements and diatomic elements and stuff, are chlorine atoms a common thing? No. Chlorine prefers to be a diatomic molecule when it's by itself as an element. Or it's going to be in another compound. So how are chlorine atoms getting into the atmosphere and messing with the ozone layer? Well, chlorine atoms get formed by the photodissociation of man-made chlorofluorocarbons, CFCs. So we make these chlorofluorocarbons. They're really good for things like refrigerants. Expand and condense, and you can cool your fridge or your car very nicely. But when those substances get into the atmosphere, they get photodissociated, meaning the light from the sun causes them to dissociate, and then there's free chlorine atoms floating around, and they're going to act as a catalyst for this reaction. So that's an undesirable reaction. Your car, since we're in California, has a catalytic converter. Catalytic converters are going to contain solid catalysts such as platinum, rhodium, or palladium on a high surface area substrate. So something that's kind of spongy looking. It's going to have a large surface area so that it can take care of more of the exhaust pollutants in a reasonable amount of time. So exhaust pollutants, nitrogen monoxide and carbon monoxide, get converted to less harmful substances, nitrogen and carbon dioxide. So those two gases are significant components of air, right? Nitrogen is the main component of air, and carbon dioxide is also a fair amount of air. So the catalytic converter, using these catalysts, catalyzes this reaction, causing it to occur faster. It also helps the complete combustion of fuel fragments. So when your gasoline is burning, ideally it would all form into carbon dioxide and water. But it's not super pure because it's not worth the effort and expense of making it super pure. So it's got other stuff in it, and it's going to have some incomplete combustion. And so you might have fuel fragments, like propane. Okay, and so the catalyst in the catalytic converter takes that and catalyzes its reaction to produce carbon dioxide and water. Read that. So inside that catalytic converter is a ceramic substrate. And I think one of the reasons that those catalytic converters are really expensive, if you've had to replace one, you know that can set you back $500 just for the piece, right? We're not talking about anybody putting it in. They have expensive metals in them as catalysts. Platinum is, I think it's more expensive than gold. Rhodium is also, and palladium. So those are high-cost metals. Yeah?
You may not know the answer to this. If the catalyst aids the reaction without being consumed, then what wears out the catalyst?
It's a good question. So if this is a catalyst and it's not being consumed, what wears out in these? I don't have a good answer for that.
It's a conspiracy from bottom.
A conspiracy. Yeah, I like conspiracy theories personally. I think the universe is conspiring against me. My guess is it's perhaps more of a mechanical failure, that there might be corrosion or leaking or something, or physical damage. That's my guess. Yeah.
How would you know if it's a catalyst? Like, let's say it's like a problem, and it says, I want you to write down the actual, equation. But, the catalyst
Well, that's a good question. So if you're looking at a mechanism, the question is, how would you know it's a catalyst? If you're looking at the mechanism, and when you add those equations, the individual steps together, oh, yeah. Oh. Yeah, so you'll know not to write it, but the difference here between this and the other ones that we looked at that had intermediates that also canceled out, the difference here is that this is the reactant. It appears as a reactant initially, and then it's regenerated. The other ones were created and then destroyed in the steps. So the catalyst is used and regenerated. An intermediate is generated and then used. Just figured that one out right now. Well, they're both going to cancel out when you add the mechanism steps together, the elementary steps. They're both going to cancel out. But we can identify this as probably being a catalyst because it starts here and then it got used up and then it got reformed. When we go back and look at one of these other things, like this one here, we've got O3. Oxygen is being formed here, but then it's being used up. So the order's different. It's being made and destroyed. A catalyst is being destroyed and remade. Okay? Two kinds of catalysis, and it just has to do with the physical states of the catalyst and the reactants. So homogeneous catalysis, the catalyst is in the same phase as the reactants. So the catalytic destruction of ozone by chlorine, the chlorine atoms and the ozone are both in the gas state. They're in the same state, so that's called homogeneous catalysis. Our example of the catalytic converter, you have the catalyst being a solid, metal atoms on a solid substrate, and the reactants are gases that are passing through. So they're not in the same physical state or the same phase, and so it's different, heterogeneous catalysis. So ozone depletion is a big topic, as is global warming, right? And I think this points out that investigating anything like this, you collect data, and then you have to look at the data very carefully, and if you have a bias, you can skew the data to show what you think it should show. And so as a scientist, I am skeptical of most of the things that show up in the news because I have no firsthand knowledge of how that data was manipulated. I don't know enough. So am I concerned about it? Yeah, global warming is not a good thing. Ozone depletion is not a good thing. Is it an urgent disaster that is impending? I don't know. Should we be careful not to emit stuff into the atmosphere? Sure. Do we need to go crazy? I don't think so. So here's an example of something. So here's looking at, this is the South Pole, and looking at the ozone thickness or concentration. And so here, it's a little bit thin down here, but this is in May, and then in September, we've got this big disturbing hole in the ozone layer, which could cause us to completely freak out, right? So this purple is the smallest concentration or smallest thickness, and green is thicker. And so there's this big hole that occurs over Antarctica. But the interesting thing that happens is that hole appears and then it disappears. The following May, it's going to look like this again. What the heck is going on? Well, it does have to do with chlorine, but why doesn't it happen everywhere? Why is it just over Antarctica? So I think this is interesting. So chlorine is evenly distributed throughout the entire atmosphere. Gases mix very well, and even in places where they don't use chlorofluorocarbons, places where we do, it just spreads out everywhere, right? So the chlorine from those chlorofluorocarbons gets bound up in substances such as ClO and O2. So the chlorine gets photodissociated. Some of it's going to go destroy ozone, but some of it gets stuck in these other compounds that are in the atmosphere. And so that keeps it from just completely tearing up the ozone. So the South Pole contains polar stratospheric clouds. So these are different than regular clouds. These contain ice particles. So the ice particles catalyze the reactions which release the chlorine from these compounds that have trapped it. So ice particles in the clouds are present in those colder regions like the South Pole. So what happens is those ice particles cause the formation of chlorine atoms. Now in the winter at the poles, there's pretty much no sunlight because that part of the earth is facing away from the sun, and so the sun never really rises, right? It's just dark all day, all night. In the summer, it's the opposite. The sun doesn't really set, and that becomes more pronounced the further you go away from the equator. So at the poles, it's at its extreme. So as the South Pole begins to get more and more sunlight, it's going to expose these chlorine molecules to the sunlight, which will dissociate them into chlorine atoms. Those chlorine atoms are going to catalyze the destruction of ozone. So as those clouds melt, and this happens, the ozone's depleted. Once the clouds melt, we don't have this release of the chlorine anymore, and the whole business stops. So we get a hole that begins to form every spring. It lasts for 6 to 8 weeks. Once all those clouds melt, then it stops and the ozone builds up again. It's a yearly thing. Any questions? I am not going to test you on Antarctic spring and the Antarctic ozone hole. I just think it's an interesting application of why do we even care about stuff like this. Did you have a question? It's just a cycle, yeah. It's just a cycle.
How do they relate this to global warming, or is this totally separate?
I don't think this really has any effect on global warming. If the overall ozone layer becomes thinner, then more energy from the sun gets through. And so you get the globe warming up. So global warming isn't good, but if you look at all of the history of the Earth and ice ages, our planet is really in a very, very small sweet spot of temperatures. So if the temperature goes too low, and it snows in the north parts and the south parts, and then it's a little too cool, and the next summer the snow doesn't quite all melt. The white snow reflects the energy from the sun, and so next year that's going to be a little bit colder. And it doesn't take much of that to make the whole place cold and everything freezes over. And so you could also descend into an ice age. So I figure what's going to happen is going to happen whether I worry about it or not. So I'm not going to worry about it because I can't do anything about it. It's just going to make me miserable, right?
That's a pessimistic.
Kind of pessimistic. It's
It's not.
pragmatic. It's practical.
Maybe it's best to, I just think it's best to not speed things up.
Well, yeah, I am definitely, we've got solar panels on our house. I'm going to take reasonable steps to avoid contributing to anything that might cause global warming. Right? Pardon me?
Oh, the solar panels are like cheaper after a while. I mean, they're expensive eating it afterwards. So,
That's a completely different subject. Oh, I forgot about this one. I thought we were done. We're not. Okay, so hydrogenation of double bonds. So this is ethene. It's got a double bond, and that can react with hydrogen, and that normally occurs at a slow rate at normal temperatures. It can be catalyzed, though, using finely divided platinum, palladium, or nickel, and that can cause the reaction to occur very rapidly. So what's happening here? The large activation energy of the reaction is due to the strength of the hydrogen-hydrogen bond in that hydrogen molecule. When the hydrogen molecule adsorbs onto this solid surface, it puts strain on the bond between the two hydrogen atoms, making it easier to break. So we've got, this is another example of heterogeneous catalysis. So we have adsorption. The reactants adsorb onto this solid surface. So the gas particles stick onto here. Diffusion occurs as those reactants can move on the surface. Let's not get too far into how they would do that, but they can move on the surface. And then you have a reaction where the reactants react with each other to form products, and then those products desorb. Desorption, they leave the surface and they go back into the gas state. So the process of being adsorbed onto this surface causes a lowered activation energy, a different sort of a mechanism. Enzymes. These, I think, are the most interesting. So I kind of alluded to this earlier. The reactions needed for your body to function, for any living organisms to function, are way too slow under normal conditions. It's not going to work. So enzymes are the name for the biological catalysts that cause all of these reactions to occur in a more expedient manner. Enzymes are usually large protein molecules. So the reactant molecule is called the substrate, binds to an active site on that enzyme, and that occurs through intermolecular forces, sometimes covalent bonding, but usually it's dipole-dipole forces, hydrogen bonds, van der Waals forces, those sorts of things. And when the substrate is attached to the active site, it lowers the activation energy of the reaction, which causes the reaction to go faster. So here we have a general mechanism. We have the enzyme plus the substrate, and the substrate is adsorbing or attaching to the enzyme, so we get this enzyme-substrate complex. And that's the fast step. The slow step is where the reaction occurs, where this enzyme-substrate complex, this substrate then is breaking into the two new products. That's the rate-limiting step. And here again we see the enzyme showing up in the mechanism, not showing up in the overall reaction, but it starts as a reactant and ends as a product. It's destroyed or engaged and then made available again. So this is a specific example, the hydrolysis of sucrose. So sucrose is a disaccharide. It's got a glucose molecule and a fructose molecule, and they are bonded right here. There's this carbon-oxygen bond that holds them together. Well, your body needs to hydrolyze them, break those two apart. It's a very slow reaction at body temperature. So what happens is there's an enzyme. Your body uses an enzyme called sucrase, and enzymes typically have names that end in ASE, and the first part of their name relates to the sort of thing that they're either the substrate or the type of reaction that they catalyze. So the sucrose molecule fits in here. It sort of comes in almost like a spaceship landing in a dock, right? Or a lock into a key, and it fits in here. But when it fits in there with its intermolecular forces attaching to the enzyme, it strains that bond. it stretches it or bends it and puts strain on it, making that bond easier to break. And that's what's lowering the activation energy and making the reaction happen faster. So without the enzyme to strain that bond, the reaction's probably not going to happen. It's going to happen real slow. Yeah.
So it lowers the activation energy by using intermolecular forces basically to just like stretch them? Like just
Yeah, stretch or bend.
So it makes the bond weaker.
Mm-hmm.
So the activation energy is less to break.
Yeah,
it.
so it's easier to break.
So then you can, under our regular body temperature, is...
Yeah, so the enzyme causes the reaction to go much faster than it would at the same temperature without the catalyst. You can speed the reaction up by heating it up, but you heat sugar up too much and it decomposes. So that's not going to work. And so your body, you get into biochemistry, it's amazing. And it's just really fascinating how your body controls all these different reactions, and enzymes are a major thing that they use to control. Any questions? Mm-hmm.
So the sucrase in this situation is the enzyme?
The sucrase is the enzyme. Yeah.
So there's different types of enzymes in our body that do different things?
Yeah, you have a gazillion enzymes in your body. Most enzymes catalyze one specific reaction, but some of them can act on more than one substrate.
And they're created in our body?
Yeah, your body makes them. So they're protein molecules. So your body makes proteins to make, build up your muscles. And so your DNA has code in it that makes the enzymes with the ribosomes and all that good stuff. And so there are genetic defects or syndromes or diseases where a person's DNA does not cause them to make a necessary enzyme. And sometimes it's just a mild annoyance, you have to avoid something. Other times it's life-threatening, fatal. Yeah, so if you're lactose intolerant, your body is no longer making lactase, which is what catalyzes the metabolism of lactose. And that's something that you're generally not born with. Your body makes lactase and you digest milk fine when you're young. And then as you get older, it's fairly common to your body just quits, because really milk was made for baby cows and baby people, right? It's not made for grown-ups. Any other questions? So, kind of a summary. Enzymes give organisms tremendous control over which reactions occur and when they occur. They're extremely specific. They catalyze a single reaction, and they can speed reaction rates by factors as large as 1 billion. It's mind-boggling. Substances that inhibit enzymes can be highly toxic. So if you ingested something that inhibited your sucrase and you could not metabolize sucrose anymore, that's not going to be good for you, right? And some of those are going to be fatal. So you lock up a single enzyme molecule, that can prevent the reaction of billions of substrate molecules, just messing up one enzyme molecule. So you get into some things that are like neurotoxins and stuff, and just a little bit totally messes everything up. There we go.